5 important properties. The first thing is the definition of a logarithm, which we talked about together in class. This is the class 35 notes that I had asked you to do on your own. So this is a really important thing. Know what a logarithm means. And then there were 4 more useful properties. We've got the log of a product. If you have the log of a product, you can break that up into the sum of 2 logs. The log of a quotient, you can break that up into the difference of 2 logs. The log of x to a power, you can take that power and bring it down in front of the logarithm, so it becomes multiplication. Okay. This one will come in particularly handy today, so we'll use this one a lot today. And then finally, we have the change of base formula, which is really helpful because you only have 2 bases on your calculator, log base 10 and log base e, log and ln. So if you can change from any base to another base using this formula, any log base b of x, you could change it to log base a, where a is anything you want. Could be 10, could be e, of x over that same base of b. All right, so hopefully you went through that, and I was thinking we would do a couple of these from the activity together, just to make sure we're all getting it. So let's look at we'll just do a few. We'll start with A. So that is log base 2 of 2 times x. So that's the log of a product. I can break that up. It's like you're distributing the log, but instead of a multiplication, it becomes a plus. That's not what's happening, but it looks like distributing. So this becomes log base 2 of 2 plus log base 2 of x. And then using the definition, what is log base 2 of 2? 1, because when I say log base 2 of 2, that means I'm asking you what power should I raise 2 to make 2? The first power. So that's why it comes out to 1 plus log base 2 of x. All right, so let's look at b here. We have log base 3 of 9 over x squared. So that's a quotient. That's the log of a quotient. And I can expand that to be the difference of 2 logs. So this would be log base 3 of 9 minus log base 3 of x squared. But what is log base 3 of 9? 2, because 3 squared is 9, right? So when I look at log base 3 of 9, I'm asking myself, what power should I raise 3 to make a 9? So my answer is a 2. And then I can apply another property of logs here, because that's x to a power. I can bring that power down in front of the log, and this becomes 2 times log of x. Log base 3, yes, sorry. So I've used all 3 properties now in these first 2 examples. Any requests? You want me to do another one? You want me to do like the most complicated one? E? Okay, let's look at E. The ln of x cubed over y squared z. So first thing I'm going to do is simplify the quotient, right? So I'm just going to do one thing at a time, and I think that's the key to these, is to not let yourself get overwhelmed by all the different rules you're going to have to apply, because you should just do one at a time and just take your time with it. So this is going to be the ln of x cubed minus the ln of y squared z. So all I did was apply that quotient, expanded it to become a difference. Ln of the numerator minus the ln of the denominator. All right, but the ln of x cubed can be simplified using one of my properties about the exponent. I can take that 3 and bring it down in front. So this is going to become 3 ln x minus. And then this is the ln of y squared z, which is a product, y squared times z. So I'm going to expand that. And I'm going to put it in parentheses here because I'm subtracting this whole amount. So I'm going to expand it, and it's become ln y squared plus ln z. So the parentheses is the key sticking point here, is that a lot of people might forget to put them. But ln y squared plus ln z is equal to ln y squared z. So I'm replacing this with this whole quantity. I need parentheses around it. Yeah, then I can bring the 2 down on the ln y squared, and I can distribute that minus. So I'd have 3 ln x minus 2 ln y minus ln z. So it's not so bad, right? Yeah. Nope. All right, let's do a couple where we condense. So we're kind of applying the rules backwards now. So if I want to do log x plus 2 log z, this 2 that's in front of the log, I could pop back up into the exponent. So this would be log x plus log of z squared. And then that's the sum of 2 logs. They have the same base, so I could condense it into a single log where I multiply those 2 inputs, x, z squared. So I'm just applying the exact same rules we were using before, but backwards, going in reverse. Log base 2 of 5 minus log base 2 of 7. They have the same base, so I can condense them into a single log of a quotient, 5/7. Yes. Yeah. All right, then we'll do one complicated one. Look at C. So I have a 1/2 in front. That means I could raise it to the 1/2 power. So this would be log base b of x to the 1/2 plus log base b of z minus log base b of w. But x to the 1/2, we could write that as the square root of x. So this is log base b of square root x plus log base b of z. You might get sick of writing these things over and over again, but like I said, just do one rule at a time. Until you've done like 5 million and you know you won't make a mistake, just apply one rule at a time. All right, so now I've got 2 things that have log base b. Right, I can combine them into a single logarithm where I multiply the inputs. So this will be log base b of square root x times z, and then minus log base b of w. And then I have the difference of 2 logs, and I can combine them into a single log by taking a quotient of the inputs. So I have log base b of square root x times z over w. Okay, so question is, what if this weren't a plus, but it were a minus? So again, I would combine them just one thing at a time, right? So first I'd pop the 1/2 up, so I'd have log base b of the square root of x minus log base b of z minus log base b of w. I'd look at these 2 first, combine them following the rule, log base b of square root x over z minus log base b of w, and then apply the rule again. So I'd have log base b of square root x over z over w. And then I've applied all the rules. It's just a matter of simplifying this compound fraction, which we have not done a lot of practice with. So let's see if we do a little aside here. Square root x over z divided by w. You can think of that as w over 1. put any number over 1. And then I would do square root x over z times the reciprocal, which would be 1 over w. So you get square root x over zw. That good? Make sense? Okay. All right, so class 36, an exponential equation. So an exponential equation is any equation that has a variable in the exponent. So we're going to solve exponential equations using 2 different methods today. The first is known as relating the bases, when you can write each side of the equation as a power of the same base, right? Then you can just set the exponents equal. So relating the bases, if you can write your equation as b to the u equals b to the v, then you can just say, oh, then u has to equal v. So if I wanted to do 3 to the 2x plus 1 equals 27, I've got a variable in the exponent, so this is an exponential equation. I'm going to rewrite that 27 as a power of 3. How could I rewrite 27 as 3 to the something? 3 to the third, yeah. So this is going to be 3 to the 2x plus 1 equals 3 to the third. Okay. So my bases are the same base raised to different powers. Then the 2 exponents have to be the same, right? So now I just set 2x plus 1 equal to 3 and solve. And I end up with 2x equals 2, so x equals 1. Check that your solution works, right? So this, if I plugged a 1 into the left side of the equation here, I would get 3 cubed. Does that equal 27? Yeah. So that's called the method of relating bases. Got it? Okay. Method 2 is where we use logarithms. The inverse of a log function, of an exponential function, is a log function. That's how we get variables out of exponents. You use a log. Because not all exponential equations can be rewritten using the method of relating bases. So for those equations, we perform the inverse function, which is to take a log of both sides. All right, so given that we're trying to solve an exponential equation that has an exponential expression on the left side of the equation with a base of e, what log base would be an appropriate choice to take the log of both sides? ln, yeah. Because we've got base e in the exponent, in the exponential expression, so I should take log base e of both sides, which is the ln. Okay, so then I'm going to use properties of logarithms to simplify the left-hand side of the equation for x. So I'm going to do the ln of e to the x equals the ln, the other side of the equation is 25. ln of both sides. ln of e to the x equals the ln of 25. Now I'm going to use one of my properties of logs that says when you have an exponent, you can take that exponent and bring it down in front. Right? So this says x times the ln of e is equal to the ln of 25. What is the ln of e equal to? 1. Yeah. And if you didn't know that, you could type it in your calculator, right? So this says that x is equal to the ln of 25. And we should check, right? So that says in my check I should do, well, e to the ln of 25 should give me 25. Just replace the x with the value, and I'll have my calculator do it. Okay, so if I type in the ln of 25, that's my x value. And then I want to raise e to that thing. So I'll do second e to the previous answer, and I get 25. That's the beauty of solving equations. You can always know if you're right. Plug your numbers back in and see if they work. Okay, so before we move to log equations, I think I'm going to do one more example of an exponential equation. Question? Okay. All right, I'm going to do one more. Let's do like 3 to the x plus 1 equals, I don't know, 18. Just randomly made up a new one. So I've got an exponent, a variable in the exponent. To get it down, I can take any log I want of both sides. I like to use the ln for everything because it's only 2 letters and it saves you a little writing. And your calculator has an ln button, which is a nice perk. So whenever I have an exponential equation, variable and an exponent, I take the ln of both sides. I use the ln. So I'm going to have the ln of 3 to the x plus 1 equals the ln of 18. And the whole point of doing that is that I can now apply this property of logarithms that lets me take this exponent and bring it down in front of the log. So I'm going to have x plus 1 times the ln of 3 equals the ln of 18. And if you just keep saying to yourself, ln of 3, that's just a number, right? This looks messy, but that's just a number. And the ln of 18 is just a number. So how would you solve this thing? Divide what?
ln 18.
Sure, I can divide both sides by ln 3. So over here they cancel. And then I have x plus 1 is ln 18 over ln 3. And then to get x by itself, just subtract 1. So x is the ln 18 over the ln 3 minus 1. What was that, Nico? Can I simplify that? Nope. I could get an approximate decimal value. ln 18, make sure you close the parenthesis if you're doing this on your calculator, or you'll get the wrong answer. ln of 18 divided by the ln of 3, and then subtract 1. And I get 1.63 approximately. So questions there? How to solve exponential equations? Take the ln of both sides. Okay, we can also solve log equations. The goal for solving a log equation is to isolate a single logarithm on one side of the equation. If more than one log appears in your equation, then you're going to use properties of logs to combine into a single logarithm. So that's why we just practiced that. And we'll rewrite the log equation as an equivalent exponential equation and then solve for x. So it's handy to have these in front of you when you're solving log equations or in your brain permanently. So I want to solve 2 times log 5x equals 4. So the domain of this thing, what values of x can I take the log of? Nope. Not 0 and not negatives. You can only take the log of positive numbers. So that means that 5x, this thing that I'm taking the log of, has to always be positive, which means that x has to be positive. So I could say 0 to infinity is my domain. So whatever you're taking the log of has to be positive. Similar to a square root, except you can't include 0, right? Whatever is under a square root has to be positive or 0. Whatever you're taking the log of has to be strictly positive. All right, so to isolate the log of 5x, I want to get that by itself. How would I get rid of that 2? I could divide by 2. So I'm going to have log of 5x equals 2. Just divided both sides by 2. All right, and then I want to get rid of the log by rewriting this as an exponential equation. Just convert this to an equivalent exponential equation. There's a base 10 there that's hiding, right? So this says that 10 to the 2 equals 5x. 10 squared equals 5x. So I convert from a log equation to an equivalent exponential equation. And then I can solve for x, because 10 squared is 100. If 100 equals 5x, what is x? X equals 20. Divide both sides by 5. And then we should check. We should check our work. Right? I go write down my original equation, 2 times the log of 5 times x, which is 20. Does that actually equal 4? Well, 5 times 20 is 100. What is log of 100? Which one? 2. The log of 100 is 2 because 10 squared is 100. So this is 2 times 2. That equals 4. Yep. So in this example, we didn't have to use any log properties to isolate the log, but often you'll have to do that. So we'll do an example where you need to do that. Everybody have this down? Okay. All right, so 2 minus log base 2 of x equals log base 2 of 4x. All right, so what kinds of x's can I put into this equation? Again, everything bigger than 0. Yep. So 0 to infinity. So I need to get all the log terms, anything that has a log in it, put on one side of the equation. So I'm going to have 2 is equal to log base 2 of 4x plus log base 2 of x. And then I'm going to use the product property of logs to combine those into a single logarithm, right? My log base 2 of 4x plus my log base 2 of x. They have the same base, they're being added, so I can combine them into the log of a product. So I'm going to have 2 equals log base 2. What is 4x times x? 4x squared. Then, once I have finally written this with a single logarithm, then I can convert it to an exponential equation. So my base is 2. What's my exponent? 2. And that should equal 4x squared. And then I solve this equation. So 4 equals 4x squared. Divide both sides by 4, and I get 1 equals x squared, which means that x equals what? Plus or minus 1. But what about the domain? Can't be negative, right? The only x's that I can put into this equation are positive, so that -1, extraneous. Let me write it better than that. Yeah, Michelle?
I missed what happened where you got the 2 squared. Where I squared.
Oh, okay. So here I have a log equation, and I'm just converting it to an equivalent exponential equation using the definition, right? So your base is always this guy. The base in the log is the same as the base in the exponential. And then this guy is your exponent, and it equals the input to the log. Yep. So just like when you're solving square root equations, because there's a restricted domain, you have to check to make sure that the solutions you come up with are actually solutions. You will sometimes get extraneous solutions.